I've just posted your last homework assignment of the semester. Homework 13 is due before class on Friday, and let me just show you what that looks like real quick. Of course, you get access to it through Blackboard, but I think I've also got it here. So it's only 2 problems. One of them is a standard step method problem, and today in class we're going to work another supportive example that I hope will remind you of the technique and process for that. Friday's class also had a standard step example. So between, I think, Friday and today, you'll be pretty well acquainted with what you need to do for standard step method. So there's that, and then the other problem on the homework assignment is related to sewer design. And we're going to talk about sewer design in class on Wednesday. So it's pretty basic open channel calculations and then a related thing having to do with water quality. But 2 problems due before class on Friday, and then on Friday what we're going to do is I just have a very basic example I'd like for us to go through together using some software called HEC-RAS. And it's software that's made available by the Army Corps of Engineers, and it uses the standard step method in the background. That's its calculation technique. And it's the software that they use to model complex natural waterways. And so if you had a channel that's meandering and changing slope and changing width and changing profile shape and didn't want to do hundreds of hours worth of spreadsheet calculations or thousands of hours of hand calculations, then HEC-RAS is software you can set up and over the course of an hour or 2 put together a really sophisticated and high quality model. So our example is going to be very basic. I'm not a power user at all of HEC-RAS. I barely ever touch the thing. But I think it's worthwhile just to see kind of where this is all heading. You know, we've talked about direct step method and standard step method, and so I think a very basic exposure to that software would be time well spent. So please have that installed on your laptop before class on Friday, and bring the laptop with you so you can follow along with the example. The next week, 9 days from today, we have our final exam. So it'll be here before you know it. It's comprehensive, and in class on Wednesday, I think I'll have some more information to share with you about the details of the final. Does anybody have any questions before we move into this second standard step method example? And depending on how quickly we get through that example, we may also be able to start on the sewer design stuff today as well. Reminder that this afternoon at 5, you're going to have free pizza at the ASEM student chapter meeting. That's just down the hall on 1201. Starts at 5 o'clock, so I'd encourage you to participate, to attend. I think I'm going to be there, so please show up. All right, so this is standard step method. Remember that the way that the standard step method is different, the need for the standard step method as compared to the direct step method is that sometimes we have gradually varying flow and also a cross section that's changing in some way. It could be getting wider or narrower, the side slopes could be changing, or it could be transitioning from circular to some other shape. But between 2 points, if we have a change in the geometry of the channel, then the direct step method won't apply. And so instead we use the standard step method. And here in this example, at the downstream location you can see it's circular with the flow depth of 1.5 meters. And then upstream we know it's triangular in shape, and so the top width is 2 times the depth of flow. And we've got some information about the distance between section 1 and section 2. It's 100 meters apart. The Z1 and Z2 is referring to the elevation of the bottom of the channel. So from that we could understand what the slope of the channel is. If we know how much the delta Z is and the distance between them, we could calculate the channel slope. Whatever this channel is made out of, it's got a roughness of 0.045, so we'd use that in Manning's equation. We know the flow rate. And then the C value talks about the energy loss during the transition. So you can think of it as somewhat similar to a local loss when we were doing the open channel flow, and it's also similar to the losses that were accounted for in open channel flow when we had a channel that was getting wider or narrower. And so it's an energy loss coefficient. So who can remember the warning that I gave you with the standard step method? There was a red alert when it came to new definitions of terms. And what's the big reminder when we applied the standard step method? What thing changed in terms of terminology?
Y1 is no longer upstream.
Okay.
Y2 is no longer downstream.
1 versus 2, right. Yeah, in the past, whenever we were saying like location 1, what we meant was the upstream location, and location 2 meant the downstream location. Here, the way that we assign the number 1 and number 2, 1 is meant to indicate the location where we know the depth, and 2 is the location where we're trying to calculate the depth. And so it's the location of the unknown. So here, in this example, 2 is the unknown, and that's the upstream location. And so let's keep that in the back of our minds as we work through the template file, that 1 doesn't mean upstream. Okay, we have the critical depth and the normal depth at location 1. So what can we use that for? If we know the actual flow depth and we know the critical depth and the normal depth, what kind of determination are we able to come up with?
Profile.
Water surface profile, right. So what we know is that the actual flow depth at location 1, where we know things, is 1.5 meters. And that's greater than both the critical depth and the normal depth. It's greater than the normal depth, and the normal depth is itself greater than the critical depth. So if normal depth is greater than critical depth, from this, we know that it's a mild profile, because it's subcritical flow when the normal depth is more than the critical depth. And then the water depth being more than either of them, let's just take a look at these profile diagrams. Oh, my computer's locked up a little bit here. That's charming. Okay. Okay, so which zone does it put us in? If we've got a mild slope and the flow depth is greater than both the normal and the critical depth, it puts us into zone 1. It's above either of them. So we have an M1 profile. In an M1 profile, it's getting shallower upstream. Now, things can get thrown off when you also have a change in channel conditions. You know, like if you had the channel section wasn't changing shape, we could say for sure it's going to be shallower upstream. But the upstream location maybe is getting wider or narrower, and so we can't always be exactly sure what the depth is going to be upstream in the same way that we can when the channel section isn't changing shape. But what we do know is at location 1, in this example that we're working today, it's an M1 profile there at location 1. All right. So the template file that I gave you last time, if you still have that available, example 1 on the bottom there was what we worked through on Friday. Example 2 is what we're going to do today. And in fact, I think maybe what we ought to do is make a couple of improvements just to simplify our calculations. If we add a couple of columns to the spreadsheet that aren't there right now, then our calculations will be easier. And so specifically what I mean is, you may recall that when we were going through the calculations that we referred to something that's known as water surface. And so water surface is the elevation of the location and the depth. And so here we've got just the depth referenced, but for a variety of reasons it maybe would be easier for us if we also had a column that was water surface. And so let's do this. Highlight everything, not the whole column, but just where we're going to do these calculations, and then right click insert, and it'll shove things to the right, and that makes space for us to have a, oh, by the way, I guess I needed to move this over too. Now we can have water surface at location 1, and that's going to be Z1 plus Y1. And so let's do the same thing for the unknown location. Right-click, insert, shove everything to the right, and then let's have the water surface at location 2. Okay? And then the other thing that was a little bit tricky was just calculating the velocity head inside of another calculation. So if we had we've got velocity as a column, but if we had velocity head, then that would also make things easier. So highlight these cells, right-click, insert, shove it to the right, and we're going to have v squared divided by 2g. And that'll have units of meters. And we're talking about the velocity at location 1 there. And then we'll also have a velocity head term here at the unknowns. Oh, maybe I should do it after the velocity. Yeah, so right-click. We may need to change some of these column widths. But in the long run, I think it'll be worth having v squared divided by 2g, and referring to the velocity at location 2. All right, so with those enhancements made, let's now start to put in what we know about this example. So the problem statement says it's a half circle, the depth is 1.5, and z1 is 0 meters at that first location. So how much flow is going through this? In this problem, it's 1.5 cubic meters per second. The roughness of the material that the channel is made of gives us an N value of 0.045. Z1, the bottom of the channel, is set as our elevation datum at location 1. So that's 0 meters. And then at the upstream location, the elevation datum is 0.5 meters. The transition energy loss coefficient is 0.2, and then the distance between the 2 points is 100 meters. All right, so we've got a circle. We're going to need to calculate the area and the wetted perimeter of the circle. Let me just on the right board write the formula for the circle. The area of a circle is pi r squared. And so for a half circle, area of half circle, which is what we've got, pi r squared divided by 2. And the perimeter of a circle is 2 pi r. And so then the perimeter of a half circle is just pi r. Okay, so we'll use that now here in the known section. Known is this location where the depth is 1.5 meters. Okay, so the depth is 1.5. The water surface equals depth plus elevation. So it's the same. Anchor the references up to the top part there. I made that mistake a couple of times on Friday, I think. Anytime we reference these cells up above the rows, then it should be anchored with the dollar signs. Okay, the area, pi times the radius. The radius is the same thing as the depth here. If we just take a quick glance here, you can see the depth is 1.5, and this is a half circle. So pi d squared divided by 2. Okay. So we've got the area. The velocity of flow, of course, is just going to be the flow rate divided by the area. So equals flow rate, anchor the reference up to the top, divided by area. So we get the flow velocity there. Velocity head will be V squared divided by 2 divided by 9.81. Okay, so we've got the velocity head. Wetted perimeter from the formula on the whiteboard, it's just pi times r, where here r is the same thing as the depth. So pi times r. Okay, hydraulic radius is defined as the area divided by the wetted perimeter. So equals area divided by the wetted perimeter. And then finally, energy is the depth of flow plus the velocity head. So equals the y plus the velocity head. Okay. What is the slope of the channel here? If the channel is gaining half a meter of elevation over 100 meters, so the channel slope is delta z divided by length. So 0.5 meters divided by 100 meters. So it's 0.005 is the channel slope. We're going to keep that in mind. Here on the template, what is the slope of the energy grade line at location 1? Slope of the energy grade line we can get from this formula. It's just rearranging Manning's equation. So equals N, anchor the reference, times Q, anchor that reference, divided by the area, divided by the hydraulic radius to the power of 2/3, so 0.6667. And then all of that is squared. So we get the slope of the energy grade line at the known location is 0.00054. And now we'll move on to our calculations for this Y2 location. So it's an M1 profile, which suggests that all things being equal, it's more likely to be a shallower depth upstream than it is at the downstream location. So let's just say, what if our initial guess is the same thing, 1.5 meters, and then what we're going to expect is that when it goes through that self-correcting process in subsequent rows, that the new depth should be probably getting shallower. All right, so water surface is defined as the depth plus the height above the datum to the channel bed. So Y2 plus Z2. Be sure to anchor the reference to Z2. Okay. Area, for a triangular section like we've got, let me write this on the whiteboard as well. So for a where it's 2 times y across the top and the depth is y, then the area is going to be 1/2 y times 2y. So it's y squared is the area. And then the wetted perimeter is going to be, this side piece here. And so the wetted perimeter is the square root of y squared plus y squared. Because it's got 1y, if it's 2y total across the top, then that means it's y here and y there. So it's just the square root of y squared plus y squared. So that is the square root of 2y squared. And that is for one of the sides. And of course, the wetted perimeter includes both of them. So the total wetted perimeter would be that times 2. So that's this, and there's 1 on either side. Okay, so the area, what we're going to use for the wetted perimeter is just the depth squared. Area is depth squared, so depth to the power of 2. Velocity would be the flow rate. Be sure to anchor the reference up there to Q, and then divide by the area. Velocity head is velocity squared divided by 2 divided by 9.81 for G. So we've got velocity squared. Wetted perimeter, it's going to be 2 times square root of 2 times y squared. Okay, hydraulic radius is area divided by wetted perimeter. And then the specific energy at location 2 is going to be the estimated depth, because remember, this y2 that we're going from is just an initial guess. So this E2 is based on the initial guess. So it is the initial guess depth plus the known, plus the velocity head. So depth plus velocity head. And now we've got that velocity head column. We don't have to embed the velocity head calculation elsewhere. Okay, so we've got the energy at 2. Okay. Slope of the energy grade line, we're just using Manning's equation again, rearranged. So it's going to be that same formula. It's N, anchor the reference, times Q, anchor the reference, divided by the area, divided by the hydraulic radius, to the power of 2/3. And then all of that squared. Okay. Observed head loss is defined as the difference in specific energies. So the observed head loss is going to be, boy, these formulas are getting a little crowded. So the observed head loss is E2, which we've just calculated, minus E1 from the knowns. Okay, and then the average slope of the energy grade line is just going to be the average of at location 1 and at location 2. So it's thought of as what's the slope of the energy grade line at the midpoint between the two sections. So equals 1 plus the other divided by 2. Does anybody have any questions so far? We can pause for a second. If anybody needs to see the calculations for one of the columns, I can go back to it. Okay. Calculated head loss. Let's go find where's the formula for that. Here it is. Calculated head loss is going to be the slope of the energy grade line at the midpoint. So this one that we've just calculated, times the length between the two sections. And so just referencing here this cell that has 100 meters, got to anchor that so it always looks in that same spot, plus the C value, refer to that location and anchor it. Okay, C value times the absolute value of the difference in the velocity heads. And this is nice again that we've got the velocity heads calculated. So the absolute value of velocity head at 2 minus the velocity head at 1. No, not the velocity, velocity head. Yeah. Okay. So the calculated head loss, 0.134. So the first thing we want to ask is, do the observed and the calculated head loss, are they equal? And they're not, so that means our guess isn't quite right. That we're going to have to go through this process and calculate a new guess depth for Y2. And the process by which we make that correction is to calculate this water surface 2 calculated. So the water surface 2 calculated is this formula. So it's the water surface at 1, which we do have here. Water surface at 1 plus the velocity head at 1, which we've also got that. Plus the calculated head loss, which we just determined here, minus the velocity head at 2. Okay, 1.62 is the calculated water surface elevation. And then the updated is just going to be the calculated, which we just came up with averaged with the previous guess of the water surface. And so the updated would be this new value we just came up with plus the previous guess of the water surface at 2 divided by 2. So splitting the difference. And just as a test of convergence, remember that we have this percent difference, which basically we're looking for that to get closer and closer to 0. For percent difference would be the updated value minus the previous value divided by the updated value times 100. And we may see that go from positive to negative. And so the fact that it's negative 10.5% difference just means that the new updated water surface is smaller than the original water surface estimate was. It's just the absolute magnitude of the percent difference we'd like to see go below 1%. But there are other indicators that the solution is converging, namely that the observed head loss and the calculated head loss will become equal. Okay, so now what we've got to do is fill in, like we want to have, the knowns aren't going to change. It's going to stay constant throughout. So 1.5 is going to be our depth every time. And all these calculated values are going to remain the same if the depth remains the same, and if I remember to anchor the things. It looks like I did. Okay, so the new guess of the depth is just going to be based on this updated water surface. And remember that water surface is defined as depth plus z. And so if water surface is y plus z, then y is water surface minus z. So the way that we get our updated guess here is we say it is this previously calculated water surface minus the z that we know for location 2. Anchor that reference there. So we're going to a new depth of 1.31 meters. So things are headed in the direction that we suspected based on the water surface profile being M1. It is going to be a shallower depth upstream. Now, I think what we can do is just basically highlight everything and drag it down a row. And as long as things were properly anchored, we should see that things are headed in the right direction, although it is strange to see the observed head loss be negative. I'm not sure what to make of that. Well, let's just see where this goes. So 1.31. Actually, now that we've defined this as being the previous water surface minus the elevation. We can select all of the row and drag it down from there. Another 1.26. You see the percent difference is getting smaller. Although I'm just perplexed about why we're getting negative head loss. I may need to look into that later, but let's just take it until the percent difference is no longer changing and see what depth it gives us. So 1.26, and that is the value that I've previously calculated. Despite the fact that the observed and the calculated head loss don't match, I'm not sure what to make of that. It could be just that I've got the order wrong in the velocity heads, but that's the process you need to follow on the homework assignment. You just go through in the homework assignment. We've got a downstream location where it's a trapezoidal channel with a bottom width of 4.5 meters and 1-to-1 side slopes. So that's, you know, the equivalent of what we've just done. Basically, the downstream location where we know things, instead of being half a circle, it's a trapezoid and the bottom width is 4.5. And at the upstream location, it's still a trapezoid, but the channel's a bit narrower. Instead of being 4.5 meters wide, it's 3.75 meters wide. There's an energy loss coefficient that's defined. You've got a channel slope that's defined, and from the channel slope that's given is how you're going to determine the Z2 upstream. The flow rate is specified, and so I kind of walk you through the same process that we've done in class just now, like asking you to determine the critical depth. You know, in the example we just did, that was already given. The critical depth and the normal depth at location 1. You're going to have to kind of refresh your memory on how to calculate the normal depth and the critical depth. I think you're probably in the mindset of the easy way to do it is if it's a rectangular channel, you know, but this won't be a rectangular channel. It's going to be, because it's trapezoidal, you'll have to set the Froude number equal to 1 in order to calculate the critical depth. Yeah?
For the Excel,
Mm-hmm.
on the second energy, don't you have to also include the Z value for elevation for E2?
E2. No, I think the specific energy is just the energy above the bottom of the channel. Let me think. Oh, yeah, you're right. Yeah, I should have actually looked here. So it's talking about total energy, not specific energy. Yeah. So it does. It makes it so that they match. So thank you for noticing that. Yeah. This isn't just talking about specific energy. It's talking about the total energy. And I should have remembered that, because if we go back to the diagram, what we're balancing here is from the datum all the way up to the total energy line. So it's not just the specific energy. Thank you. So yeah, if we, the reason why it didn't matter here is because the Z1 was 0. But I guess to be technically correct, what I ought to do is I ought to say plus whatever the Z1 is. Doesn't change a bit. At least now I'm being consistent. And then here for E2, what he noticed is in the formula it tells us it should be depth plus velocity head plus elevation. Anchor the reference. And so if we drag that down through all of them, then yeah, that does account for why the observed and calculated now are converging, and it didn't change the depth, but at least it gives us that confidence that not only is the elevation stabilized at 1.26 meters upstream, but also the observed and the calculated head loss match.
How would that not throw off the answer?
What's that?
How would that not throw off the answer?
It's because when we were doing our calculations, these water surface calculations already take the Z into account. So like, you know, the adjustment thing, the adjustment engine that's working in the background, this water surface has the Z's built in. So it was just the indicator. Like The reason we calculate this head loss is as an indicator. It's not because this value is being referenced elsewhere. It was the calculated one that was being referenced, and that's the one that wasn't one that relied on the E2. All right, so that is what you're going to do on the standard step method. Homework problem is critical depth, normal depth, calculate the water surface profile, just like we did, and then make an initial guess of whether it's going to be getting deeper or shallower upstream, with the understanding it could be different because of the changes in the shape of the upstream. It's narrower. And then basically find the depth and the water surface elevation at that upstream location where the depth isn't known. All right, so now let's talk about sewers. And sewers are interesting for two main reasons. One is that there's a biological component to what's going on. And we don't talk about biology much in hydraulic engineering, but this is a rare case where the hydraulic engineer has to know a little bit about the water quality and the effect that it could have on the infrastructure. Because wastewater supports microbial respiration, and one of the constituents in wastewater typically is sulfur. And the bacteria that are breaking down biochemical oxygen demand in wastewater are also reducing sulfur, and it forms a corrosive and poisonous gas known as sulfur dioxide. Hydrogen sulfide. Sulfur dioxide is something separate. Hydrogen sulfide. So basically in sanitary sewers, what we have to do is hopefully provide a way for water to flow by gravity, the wastewater to flow by gravity from people's homes towards a collection network. And it's often concrete pipes because concrete is resilient, lasts a long time, and it is fairly resistant to corrosion, and it also is going to be less prone to groundwater, causing it to float upward if it's buoyant conditions. If the groundwater is above the sewer pipe, sometimes plastic pipes can be forced to the surface when the groundwater table is high. But what we're looking at is a cross-sectional view of a sewer pipe at a manhole location. And manholes are just locations that are provided for you to get access to the pipe so that you can do inspection, cleaning, and repair if needed. And service connections are the lateral pipes that are bringing flow from a commercial location or somebody's home into the pipe. And occasionally, depending on the topography of a town, it may be necessary to have lift stations where water is pumped by pressure from a lower elevation to a higher elevation so that then it can continue onward beyond there by gravity. So pump stations are not desirable from a cost-saving standpoint because it's expensive to maintain the pumps, it's expensive to pay for the electricity to lift water, very costly. So if at all possible, you want to design the sewer collection network to avoid the need for pumped flow and instead just have everything flowing by gravity. And when sewers are put into place, it's really important to make sure that they're sized with an eye towards the future. Because if you only accommodate the flows that are currently present in a location, then it's very likely that in the short term you're going to run out of capacity in the pipe. And that's one of the problems here in Huntington, is that when a lot of the pipes were put into the ground, there was less impervious area than there is now. Like roads were narrower. Oftentimes they were like gravel roads instead of paved roads, and so there's a lot more stormwater runoff entering sewer pipes now, and there's more people living in places, and people use more water than they used to. So just for a variety of reasons, a lot of the pipes in Huntington are undersized compared to what we would probably put in the ground today. Some sewers are operational after more than 100 years, and so that's why it's so important to think towards the future. And part of the thing that complicates the situation is that it's not a constant flow rate that's getting into the pipes. There's a big variation in discharge into the pipes, and you've thought a little bit about temporal variation in flows for the project, but you were thinking it from the standpoint of temporal variation in water demand. So that's the water going to the house. It's going to be more in the evening, for example, than it is overnight. But then think about the water that comes to the house. A fraction of that is going to end up in the sewer. Most of it, actually, is going to end up in the sewer. And so if people are using a lot of water at 7 or 8 p.m. as they're washing dishes, taking showers, cleaning, and so on, a lot of that's going to be getting into the sewer, but then the flows are really low overnight. So there's a big variation in flow, and there's different empirical equations that have been developed in order to try and speculate on the ratio of low flow to average flow, and to speculate on the ratio of peak flow to the average daily flows. And then on top of that, the human behavior variation, there's also the fact that some sewers are receiving stormwater flows directly and intentionally, and then some sewers that are supposed to be sanitary only and they're not combined sewers that are intended to have stormwater, some of them receive stormwater just on an accidental basis because maybe there is a damage to a manhole cover, or it could be that there's a pipe crack, or somebody has connected an illegal roof drain or an illegal foundation drain. So infiltration and inflow are additional increases in the water that's getting into a storm sewer that also add to how much capacity you have to allow in order to ensure that you don't have wastewater backing up into people's basements. And that can be the consequence of an undersized pipe, is that water backs up and it flows into the low point of somebody's house, and it's really a bad look for a city when a homeowner has thousands of dollars worth of damage and kind of a contaminated living space due to sewage getting in. So a lot of times in engineering we do designs based on first principles and based on actual calculations of what's really going to happen, but sometimes we do our designs just based on codes. And the codes may have some basis in reality, but it can vary a lot from place to place. And this figure kind of illustrates there are a lot of different municipal regulations that say how much capacity you have to build into the sewer. So just as an illustration of how much that can vary, in the city of Milwaukee, what they say is that you should have enough sewer capacity to accommodate 1,000 liters per person per day. That's how much water they think is going to get into the sewers, 1,000 liters per person per day, plus additional flow capacity for inflow and infiltration. Whereas other places maybe have much lower flow rates. Berkeley, here you can see, that's only about 1/3 of the assumption that Milwaukee suggested for flow rate capacity per person. And so most likely the sewers in Milwaukee are going to be more expensive to install and maintain and operate because they're going to be really large if they're going by that 1,000 liters per person per day of how much capacity that they want to put in. Now, this is an old reference, by the way. This is from 1982. And so it could be that these are no longer the exact values, but the underlying principle is that it's a government policy that you have to be aware of, and that can drive the sizing of the sewer as much as anything else, is just what the regulations say rather than what you think people are going to be putting into the sewer. And so they'll figure out how many people are going to be living in an area and speculate into the future what its build-out capacity is going to be, the number of people, and then use whatever the policy tells them to assume for the flow rate. And the same things are used for commercial and industrial areas where on a region or local basis there are rules in place that say how much capacity you should provide in the sewer for commercial connections and industrial connections. Some facilities, particularly food processing plants and feedlots and slaughterhouses, may have their own wastewater treatment plant that doesn't have to be accommodated by the municipal sewer. So you have to kind of be aware sometimes of what kind of an industrial facility it is to know whether or not you've got to size your whole sewer network for that location. So peaking factors, let me just jump straight to the table for these equations for the peaking factors. If you know the population of the area, what these peaking factor equations say is that the larger your population is, the smaller the peaking effect would be. And that's for two reasons. One is that for a large population, you're more geographically spread out. And if you have a geographically spread out pipe network, then it takes travel time for when someone flushes the toilet, water's not moving very fast in these gravity flow pipe networks, usually 2 or 3 feet per second. And so that routing effect, the delay that occurs when someone flushes the toilet and the water has to travel a long distance to finally get to the treatment plant, a bigger population means that the peaking factors are smaller than if you have a small population where people are living closer together, then the peak effects can be more dramatic in small populations. And that's, if you put the population in here and you know the average daily flow and you want to calculate the peak daily flow or the minimum flows, then small towns are subject to more peak effects also because people tend to have more similar working schedules in small towns compared to a big city where you've got a variety of industries and a variety of working hours. The larger the city, usually, the more likely it is that people will be working on split shifts or that certain industries are running round the clock, and that throws off the same kind of synchronized work schedules that leads to synchronized flow demands entering the sewer network. So here's what's tricky about the pipe hydraulics is it's a circular pipe, but it's not flowing full. Most of the time, like it'll only be full just for a few moments each year. But most of the time the flow is less than full, and so the water is partway up in the circular pipe. And so calculating the wetted perimeter and the area is a little bit tricky. And the way that we do it is by measuring the angle that we make from the center of the pipe down to the water surface. And so the angle there is measured in radians, and if we do that, then we can relate the depth of flow to the diameter, and we can calculate the cross-sectional area on the basis of what the pipe diameter is if we know how full it is. And so, for example, if it was halfway full, then it would be pi radians. And it would be 2 pi radians if it was all the way full. So we've got formulas to allow us to calculate a wetted perimeter, top width, and area. And we'll go through an example in class on Wednesday that allows us to do that. But the last thing I want to show you here is what Manning's equation looks like. If you've got a pipe that's only partly full, then we can express Manning's equation in terms of what's the angle that the water is making, and the typical parameters that we'd have in Manning's equation, like the roughness and the flow rate, the diameter, the slope of the pipe. But it's going to be a little bit tricky for us to determine that angle theta. And another thing that's also a complicating factor is that the n value isn't constant in the same way that it has always just been a constant for us. As the flow depth changes, so does the n value, because the ratio of wetted perimeter to cross-sectional area changes a lot as a pipe goes from barely full to all the way full. So there's this figure here that we use to find out what Manning's n should be as a function of what Manning's n would be if it was all the way full. So let's leave it here for today, and remember that homework's available now for you to get started on the standard step method problem. So I'll see you in class on Wednesday.